A key theme in 5G and beyond is increased flexibility. New use cases beyond just enhanced mobile broadband are now being considered, such as ultra-reliable low-latency communication and massive machine-type communication. Each of these have different targets and priorities. They put a unique pressure on the wireless system designer. It may not be possible to design for all of these targets simultaneously, especially in hardware. However, software can provide the necessary flexibility. The question is, can a software-based solution also provide the necessary performance? In this talk, we will explore an important example of this problem for 5G and beyond, and that is the error-correcting codes. I will be presenting our paper titled GPU-based LDPC decoding for vRAN systems in 5G and beyond. I am Chance Tarver, and I will present this work on behalf of myself and my colleagues Matthew Tonmaker, Hal Chen, Charlie Zhang, and Joe Cavallero. Myself and Dr. Cavallero are from Rice University, and the rest of the co-authors are from Samsung Research America. So I will begin the talk by presenting a background on LDPC and 5G, and so we'll explain error-correcting codes and the overall structure of LDPC. I will then introduce our GPU-based software solution, and we'll use this to motivate a larger virtual radio access network vision for 5G and beyond. We will then show results showing the maximum LDPC decoding throughput that we can achieve with our system, and then we'll also show results showing the lowest possible latency that we can achieve. Again, highlighting the fact that the GPU, depending on how we deploy it, can actually be flexible in a dynamic runtime manner where we can target throughput or latency. And then we'll show our GPU system being integrated with a software-defined 5G platform known as Open Air Interface.
In wireless communications, as we send bits across an imperfect wireless channel, we expect some bit flips to occur. And so the way we deal with this is we add additional redundancy in the form of an error-correcting code. Consider, for example, that we have bits that we want to send in the form of this vector S. To be able to overcome any imperfections in the channel, we might add some parity bits, here shown as W. There are many ways that this can be done, such as turbo codes, Hamming codes, Reed-Solomon, but in 5G, low-density parity check codes were chosen for the data channel, whereas polar codes were chosen for the control channel. LDPC codes are a form of linear block codes, and so what that means is there is a parity check matrix H, and whenever we multiply H by some sort of valid code word, then we have to get 0 out of that. And so the key property of LDPC is that this H is sparsely filled with ones, and so this is the low density component of the LDPC code. Determining if a received code word is a valid code word is as simple as performing this sparse matrix vector multiply. If it is not a valid code word, then we need to perform LDPC decoding, and for that we turn to the Tanner graph. The Tanner graph is a visualization of the parity check matrix H. Each row in H becomes a check node, each column becomes a variable node. Each one in the parity check matrix becomes a connection between the check node and variable node corresponding to the row and column of the one. To decode, we can send messages back and forth across this graph through a procedure called belief propagation. We begin with the variable nodes initialized to the log likelihood ratios received from the demodulator. These LLRs will be sent to the check nodes. Each check node will consider all of the LLRs sent to it and will respond to each variable node. Each variable node will use all of the received messages from the check nodes to update its estimation of the LLR. This can be done iteratively for a fixed number of iterations, or can be done until the LLRs converge to a valid code word. LDPC has been used in other standards such as Wi-Fi. However, there are more configurations of LDPC in 5G, making it a larger challenge for implementation. In 5G, there are 2 base graphs, from which there are 8 different reconfigurations that can be performed. Each base graph can be expanded to fit a variety of block sizes through a lifting factor, with many possible values between 2 and 384. In this slide, I show a configuration of base graph 1, where the red lines represent ones in the parity check matrix H. In its largest form, we have a rate 1/3 code with nearly 18,000 rows and over 26,000 columns. This massive size also creates a challenge for implementations in that keeping track of all of the log likelihood ratios and messages between check and variable nodes, potentially for multiple users and code words, will require gigabytes of space and fast memory bandwidths to be able to meet decoding throughput targets. So as I've already pointed out, the reconfigurations of LDPC pose a challenge for 5G LDPC implementation. We also have competing performance targets for enhanced mobile broadband, ultra-reliable low-latency communication, and massive machine-type communication. To address the flexibility requirements in 5G while maintaining high performance, we utilize GPUs to create a reconfigurable platform for LDPC decoding. GPUs provide multiple advantages over platforms such as FPGA in that they are relatively low-cost, commercial off-the-shelf commodity parts that can provide high performance through software-based programming. This lends themselves nicely to a more rapid development cycle and more flexibility. GPUs are a possible part of next-generation virtual radio access network or vRAN systems. In a vRAN system, there could be a single cloud data center serving a geographic region. The hardware compute resources on the cloud, such as GPU, FPGA, and CPU, can be virtualized to provide computing for many users. With virtualization, we get the benefits such as load balancing and the ability to target multiple radio access technologies, such as 4G, 5G, and any future standards. For each standard, we can provide specific slices with different hardware resources depending on the optimization priority, such as latency or throughput, of the slice. This may seem abstract, but it is becoming a reality at Rice University through the Reconfigurable Ecosystem for Next Generation End-to-End Wireless, or RENEW project. This project is creating multiple massive MIMO radio heads and developing a campus-wide infrastructure with a centralized compute center connected to remote radio heads by fiber. A natural question to ask is why GPU? GPUs have on the order of thousands of computational units. In the case of NVIDIA GPUs, these are known as CUDA cores. This creates a highly parallel platform that can be programmed in a single instruction multiple thread programming paradigm. Since in communications we often want to perform similar processing tasks on multiple bit or multiple IQ samples, there is a natural fit between communication algorithms and GPU processing. GPUs have previously proven themselves for computationally demanding tasks in machine learning. However, those tasks are typically not real-time, whereas communication does have real-time requirements. Recently in the literature, there has been an increase in GPU processing for communications. Examples of this include turbo and LDPC codes. However, this is the first work where LDPC has been implemented for 5G on GPU. GPUs have also been recognized for massive MIMO precoding and detection, as well as digital predistortion for correcting power amplifier nonlinearities. NVIDIA has recently recognized a potential market for GPU-based computation for communications and created a dedicated SDK called Ariel for 5G virtual radio access network systems. GPU functions are written as kernels, and our implementation utilizes 3 kernels. We have check node and variable node processing kernels. Then, before sending the data back to the host, we make a hard decision and pack that hard decision into 8-bit words to send back to the host in a bit packing kernel. This reduces the total memory transfer, which is one of the main bottlenecks in GPU computing. We utilize multiple optimizations in our architecture. The optimization that contributes the most is reducing the bit widths of the log likelihood ratios. Instead of utilizing floating point data types throughout, which are 32 bits per word, we reduce the precision to 16-bit and 8-bit data types. This can reduce the data movement by a factor of 4 and provide a significant increase in speed with negligible harm to decoding performance. We also cache parity check matrices in constant memory, where they can be accessed quickly by the device. We decode multiple code words at once to better fill the GPU blocks, and we utilize GPU streams to allow the GPU to be decoding one set of code words while transferring other code words in and out. The overall architecture can be seen here. The 3 kernels are shown on the bottom, and we will go through each of them on the following slides. The parity check matrices are stored in constant memory. There is a row major and column major version stored for the check node and variable node respectively, to allow for sequential memory accesses by each kernel. The log likelihood ratios for multiple code words are passed to the device over a bus. This and the belief propagation messages are stored in global memory as either float, half, or char data types. We pass multiple macro code words with a certain number of code words per macro code word to the device. Code words within a macro code word will all execute within the same block on the GPU. We implement a scaled min-sum algorithm for our belief propagation. The min-sum algorithm is a simplification of the sum-product algorithm that converts it to only require additions and compares at a minor performance cost. By adding a scale factor, shown here as gamma, most of that performance loss can be recovered. Each check node will receive messages from connected variable nodes, shown here as Q. To each, it will respond with a message R. The check nodes load the log likelihood ratios from memory. Each thread will work as exactly one check node. We structure the GPU blocks to align with the quasi-cyclic nature of the LDPC parity check matrix. Each thread will perform the 2min algorithm for computing the messages to the variable nodes. This requires 2 recursions. In the first recursion, the check nodes read the incoming messages and keeps track of the current minimum and the second place minimum. In the second recursion through the connected variable nodes, it computes the messages to the variable nodes according to the equation on the previous slide. We will also store the change in the message for the variable nodes in the array dt. The variable nodes will load this change in messages directly and use the value from all the connected check nodes to update the log likelihood ratio. We again structure the CUDA grid so that blocks fit the quasi-cyclic structure of the parity check matrix. Each thread will be working as one variable node or column in the full parity check matrix. After iterating between check and variable nodes, we run the bit packing kernel to make the final hard decisions. We run the hard decision only on the information bits, ignoring the log likelihood ratios from the parity bits. We then store 8 hard decision bits together into char words. Compared to other LDPC implementations in the literature, which transfer all of the final log likelihood ratios to the host to make the hard decision there, this reduces the final memory transfer by a factor of 24 in the case of a rate 1/3 code. After implementation, we first compared the performance to open-air interfaces implementation. We used 5 iterations and compared to OAI's min-sum algorithm, which also ran with 5 iterations. We can see that the float and 16-bit formats have nearly identical performance. When we transition to 8 bits, there is a slight gap in decoding performance, as there is additional quantization in the LLRs. The gap between our GPU implementations and OAI's software implementation can be attributed to the difference between a min-sum algorithm implementation and scaled min-sum algorithm. We then tested the throughput versus the data type across various generations of NVIDIA GPUs, with the 980 Ti being from 2015 and the Titan RTX being from 2018. We configure the CUDA grid in this case to transfer many code words to the GPU at once and decode many simultaneously to try to target a high net throughput. We see that in the case of 8-bit char formats on the Titan RTX, we see nearly a 4 gigabit per second code word throughput, nearly double the result when performing the same tests with floating point data types. For this test, the char data point corresponds to an average latency per code word of 700 microseconds. If we reconfigure the CUDA grid to utilize the parallelism across one code word to target latency, we can run a similar test to see the best possible latency. Here, lower is better, and we see that in the case of char formats on the most recent GPU, we can achieve an average decoding latency per code word of 87 microseconds for 5 iterations. We can see that there is a small improvement as we sweep data types and that there is a significant change in performance per GPU generation. We then integrated our GPU decoder into OAI's 5G NR RF simulator. For this test, IQ data is sent over an Ethernet backhaul. In this slide, we show screenshots from that test, where the left-hand side shows constellation from the physical channels, and the right-hand side is the console output. As a sanity check, we included a message in our code to guarantee that we had integrated into OAI. After running the decoder, we are able to see that the CRC for each segment passes, indicating correct decoding. When comparing latencies, we found that the GPU was able to outperform the pure CPU implementation from OAI by a factor of 17. In conclusion, GPUs provide a flexible yet powerful platform for rapid prototyping in research systems and provide a possible long-term implementation option for virtualized radio access networks. In this work, we showed 4 gigabit per second decoding of the largest 5G LDPC parity check matrix, which was one of the highest throughputs in the published literature for this code, while simultaneously having a competitive latency. Going forward, we hope to run these tests again on the latest generation of GPUs and are optimistic and expecting significant gains due to increased memory bandwidth in the latest generation, which will make the GPUs even more compelling. Moreover, we hope to be able to integrate other physical layer tasks such as DPD and massive MIMO detection so that we can fully develop a software-defined virtual radio access network solution for 5G and beyond. Thank you.